Fine. Okay. Any questions? So do you have slides on the videos? No, the Zoom. So that it shares the screen. Yes, I can turn it here.
Do I need to mute?
Yes. That's for the.
Yeah.
Yep. I don't care. Review share.
Oh, sure.
Perfect. I hope everybody have notice of the rule change. And we start. So welcome Yicen and Ruiyang, who are Anastasia's PhD students. And they will talk about a paper that's coming up in a week or something like this.
Yeah.
Yes, please go ahead.
Sure. Thank you very much for coming this meeting because it's a very cold Monday morning. Thank you very much for being here. And I'm Yicen, and today, along with Ruiyang, and we are very excited to share with you our latest research about neural operators can discover functional clusters. And this was a collaborative work together with Antonio as well as Martin, and who are from Rice University. And basically, in this project, we aim to develop a theory as well as a feasible neural operator framework for functional data clustering, especially for ODE trajectories. And so this is our outline today. So basically, we will start from some background, introduction, problem formulations. Then I will hand over to Ruiyang, and he will provide some explanation to the theory. And there's no heavy math, and we're just trying to introduce what's the idea and the idea behind the theory and what we're trying to do with the theory. And then we will move back to return to experiments. And here I would like to show you how we implement such a neural operator for functional data clustering, and then how we conduct experiments on the proposed dynamical data sets. Okay, so let's start it. So first of all, I'd like to specify the data type we are interested in. So in lots of scientific domains, such as physics, chemistry, biologies, and including finance, numerical calculations, the data often come with as trajectories, as functions. They are not they are not vectors or points. Instead, they are functions resident in the infinite dimensional space, rather than static vectors or points in a finite Euclidean space or something. So which makes functional data clustering totally different than clustering vectors or clustering points. And one may ask, so why?
Question.
Yeah.
Anyway, we have a tradition that we know.
Oh, sure. Okay, understood. Yeah. So
you mentioned the ODs.
Yeah.
And yet the state space is infinite dimensional. Why? I mean, normally you would expect the state space to be finite dimensional for a solution of an OD.
Yeah, the solution. So yeah, so we're just trying to. So in this work, we just so we take the ODE as a special case. Like there are lots of functional data, And we're trying to study the question if we can provide a method to perform clustering to identify the latent partings to this functional data. So that's where I'm interested in. And this is the problem I want to ask, like why we want to clustering trajectories. Suppose because in our study, in our research, there are this is the problem that we cannot always avoid. Like because sometimes we have a very dirty data, very unclear data, very mixed data, which consists of thousands of trajectories.
Well, my question is
Yeah.
the following. So if you get an ODE,
Yeah.
then typically the solution of an ODE at a given time
Yes.
is characterized by finite dimensional vector.
Yeah.
Typically, we can think about this, that it lives in Rn.
Yeah.
My question is, why do we need an infinite dimensional Hilbert space functional space to describe those solutions? Because normally finite dimensional objects, they're normally finite dimensional objects.
Yeah, but this is the question, because we cannot always use the finite dimension the solution to approximate the true cylinders. Because the abstract functions, the abstract cylinders of the function located in the infinite dimensions. So that we need, indeed, in practice, we take our clustering in finite space, but the real cylinders of the function located in infinite dimensions, we cannot use. So we need to.
Yeah, that the infinite dimension is on the discrete nature of time. It's not that at each time your field is has value in a finite dimensional space.
Yeah.
Right.
Right. Yeah. So okay, let's back to the. So yeah. So this. So we want to. So we mentioned. So we want to find out like if there exists cylinders of them, so that we can use our clustering pipeline to identify the possible latent physics partings of it. But however, there's a challenge. There are some challenges for the existing functional data clustering pipeline, as well as a gap that we aim to address. So, like for the traditional functional data clustering perspective, like the FPCA or the B-splines methods, they relies heavily on the dimensional reductions. So, such as for the FPCA, you need to choose the top K components. For the B-spline, you need to specify the number of the splines. So they may effectively construction, but they often lead to a suboptimal performance because you need to discard, since you need to choose the top K, where you need to choose the number of splines, you need to discard some low, the fine-grained informations. So which will lead to a suboptimal performance.
So what does ADC stand for?
Sorry?
What does ADC stand for?
FPCA means a functional principal component analysis. So it means like you can perform.
No, the one the first one, traditional ADC.
Oh, sorry. Functional data clustering. Functional data clustering. Sorry about that. And for other aspects, the modern deep learning techniques. So like there have been also work study on established on neural operators, but they focus on regression tasks. They want to use neural operators to solve PD or solve ODE. They focus on regression. They focus on approximation. They focus on prediction. But as far as we know, there's no specific framework to connect neural operator and functional data clustering. And on the other hand, for the deep clustering methods, they pay more attention on other domains, such as image clustering, text clustering, but not on functional data. So we notice that there is a gap. It is still unexplored that whether we can use neural operator to help us in functional data clustering. And so here comes to our objective where we're trying to find out a theory as well as a feasible framework to help us to identify the latent dynamic structure, so that maybe we can use this method to help us to distinguish like the trajectory where the ODs are generated by linear problem or nonlinear problem, or it's generated by initial value problem or the boundary value problem system. And so I'd like to start by formulating the ideal case. Now, it will be much more easier if we can directly perform infinite dimensional k-means on the financial space, functional space. So like suppose we have a set of functions like G1, Gn, Gk, and they are observed trajectories, so that we can use such a infinite dimensional k-means to find out the cylinders by minimizing the expected square of the hyperspace distance, so that we can ideally get some optimal centers. And these centers will induce partition of the domain into k disjoint clusters C1, Ck. And specifically, the k's cluster of this ideal k-means is defined as a closed set of the functions nearest to fk and to any other centers. So that if we can directly perform k-means on the function data, we can directly get the centers and mission complete. So that we say that, okay, we have already find out the centers. But however, the challenge is that there's a learning problem. It's like we cannot really find such a centers. There exists a computational hurdle. The optimal clusters centers fk are abstract functions in an infinite dimensional space. So they cannot be exactly computed or analytically represented in practice. But this provides ample opportunity for us to introduce neural operator, to introduce an indirect way to solve the ideal k-means method in the infinite dimensional space. So that we want to learn a neural operator that learn the maps between the function space and the cluster space, so that we can directly get the cluster assignments from the outputs of the neural operators and then define the clusters via soft assignments mechanism. So basically, we are trying to learn a neural operator and it outputs a score, a probability. So for each trajectory, it will output some probability that this trajectory belongs to the K's clusters. And then we just need to threshold in the scores, then we can get the learned clusters. We can use this way to learn such a clusters. However, this brings another challenges, the convergence challenges. Because we don't know whether this kind of neural operator using neural operators guarantees that such a learned cluster converges to the true partitions in the ideal k-means. We only know like, okay, you give me one trajectory and I return one score, but it doesn't mean that we can learn the boundary, the decision boundaries. So that in other words, this is the set valued convergence form. So the infinite dimensional space, the pointwise convergence of such an operator does not automatically imply that the convergence of decision regions Ck. So in other words, a good function approximator is not necessarily a good classifier. So we need to address this issue.
Excuse me, one basic question. So you mean after knowing the trajectory, you find which cluster is belongs to?
Yeah.
So then when we know the trajectory, why do we need to know the cluster? What is the aim of doing this cluster?
Yeah, because as I mentioned, like for example, you have some because we want to use clustering to learn to understand the latent part of the ODs. Like suppose you have weighted source of ODs. They are generated by different equations, different systems. You need a way to determine which trajectory belongs to which system.
But now I know the whole trajectory, right?
Yeah,
So then I know everything.
but it cannot be generalized. Like you can learn a operator to help you to perform clustering. Okay, yeah, that's a good point.
So do you need to, do you need to ask them anything about the regularity of those objects? The regularity of those functions?
Yeah, we do.
I imagine the problem could be completely different depending on, what
Yeah.
regularity you require, right?
Yeah, there are some lots of conditions regarding our theory, like to meet all the convergence problems. And so that's okay. Okay, so yes, to resolve that issues. So now we have to introduce to resolve that issues, we need to demonstrate that neural operators are theoretically viable for this clustering task. And in our theory, we show that given a sufficiently expressive neural operator, the induced neural clusters converge to the true cluster induced by the k-means in the upper Kuratowski topology on subsets of H. And this is how we did to show the clustering theory. So we established the mathematical foundations for learning cluster basically in 3 steps. In the first steps, we try to show you and prove that clustering geometry in the function space. We firstly formalize the k-means, and then we characterize the geometry of the without invariant partitions. And the second step, we want to show the topological consistency of the cluster boundaries. And the last step, we propose a neural operator named sampling-based neural operator, which can be used to perform universal clustering for remaining nodes. And so in the next, I'd like to hand over to Ruiyang, and he will provide some explanation on how the theory works. Okay, I will hand over to Ruiyang.
So yeah, hi everyone, my name is Ruiyang. And Yicen basically covered some of the topics that I will cover. So I will basically give you a quick high-level walkthrough of the mathematical method. Yeah, okay, so here's our setting. We are working in a Hilbert space H, and this Hilbert space is not just any Hilbert space, it is an RKHS, which is this means, I haven't seen this. So this is one kind of Hilbert space which we work with, and one property of this RKHS is that it has some kind of regularity, which partly answers, I guess, the question that Bartek came up with, which is that, okay, so the definition is that so what does this mean? It means that for every function in this space, this point evaluation map is a continuous linear function. So it's bounded and it's linear. So one can imagine that if f is so one immediate consequence is that convergence in norm. So remember that each point in this space is a function. So one immediate consequence is that convergence in norm implies uniform convergence. So another property is that we can immediately see that the Dirac delta is an equal function in this space.
So this capital X, it's the domain of the condition, right?
Yeah, it's each point in our Hilbert space H is a function, and its domain is the capital S.
Okay.
So we can immediately see that the Dirac delta is a legal function in this space. So for example, if we have, this is our F, and if we want to evaluate a point in here, we can simply take this, relatively speaking, regular function without having to refer to this very peculiar behaving Dirac delta. So basically the intuition is that RKHSs are usually more regular and more regular than general Hilbert spaces, and it tends to be, it's usually not extremely large. So later we will see that our assumption for this RKHS is that it admits a sequence called CIS, which we will use to
So I'm still not sure I understand the definition of your, because it looks like you define the space in terms of its node. Usually you define the node in terms of the states. Or what is exactly the definition of your space H?
Well, H is a Hilbert space which has the property that this point evaluation map is continuous and linear for every x inside the domain. So this is the original definition of the reproducing kernel of this space. And I was just showing several immediate consequences of that.
So does this imply the particular structure of the node?
Yes, so for example, convergence norm implies uniform convergence. And yeah, the intuition is that it has some notion of smooth inside it.
So what would be an example of the normal expansion which is in the RTHS and when there is no?
So for example, if so basically one example is the what is called the band limited Fourier series. So these are the Fourier functions whose Fourier transform is bounded. So whose frequency is bounded. So we can imagine that we do not have extremely high frequency components like that. So for example, in L2, point evaluation is not even legal. We can have this spikes even when f norm of f is, let's say, uniformly 1, but we can have this arbitrary high spike. So this is not allowed in reproducing Hilbert space, kernel Hilbert space.
And so present H1 in 1D would be reproducing from Hilbert space.
I'm sorry, H1.
H1 in 1D, so you do have a pointwise definition. H1 of R.
Oh,
or of 0, 1.
It looks like so. I think so, but I haven't looked at it in detail. Yeah, I think it is. I have to check the detail.
It's gonna be 0.
So yeah, so basically this is one key assumption, which is that our Hilbert space is somehow more smooth than general ones. Okay, and so this is the basic working space. And how do we represent our classes? This is basically the Varane cell defined here. So each Varane cell, the kth Varane cell is defined as the set of all f such that the kth center is the closest center to it. And each Varane cell is a non-empty closed subset which form a partition of K and H, well, almost disjoint partition. Right. So using this formulation, we're able to turn the classical norm minimization problem into a set value problem, as Yicen mentioned before. So we have to define a notion in this new setting of convergence. How do sets convergence for another set? So a natural idea would be to use standard metric as such as the household distance. But the problem is that so for example, this household distance usually becomes ill-defined for infinite dimensional case. So for example, the household distance of two unbounded sets are usually always unbounded, even when the approximation looks as intuitive. So this is where this what's called the proper Kuratowski convergence comes into play. So this notion of convergence is specifically designed to prevent type 1 error. So we do not want any false positives. And the intuition is that if a point is, if the sequence of sets Cn gets arbitrarily close to a point infinitely often, then that point should be included in the limit set C. So here is the mathematical definition. I won't go through this, but I will give you an equivalent, the more geometric definition. So if this is a point in our Hilbert space X, then if it has the property that for arbitrarily small neighborhood around it, the sequence of Cn touches this neighborhood infinitely often, then this point is included in the limit set C. So conversely, the limit set C is the set of all such points that have this property. So this is basically what this slide is saying. Okay, so now we will look at how to discretize the infinite dimensional space H. So we will use the sequence called CIS, complete interpolating sampling sequence. So it has two parts, interpolating and sampling. So with the sampling means that this inequality holds. So it is saying that the information of F, well, intuitively it's saying that the information of F can be recovered by its evaluation at these axes, possibly up to the sorting factors. And interpolating is saying that, okay, for any given sequence of target values, we can find an F such that it assign these values to each of the X. So basically it's saying that the sequence of X lambda is somehow independent, so that you cannot infer the information of F at one X lambda from the information of F at the other X's. So basically, looks like some kind of basis. It's sampling means that the sequence of X's is rich enough, and interpolating means that the X's are independent. And CIS, complete interpolating sampling, simply means that the sequence that is both sampling and interpolating. And from now on, we will assume that our Hilbert space, or more specifically, RKHS, has at least one such sequence, such CIS. Okay, so now we're in a place to introduce our main construction, which is called sampling-based neural operator. And this is basically ReLU NLP on top of this sampling operator. So this sampling operator is obtained by doing inner products of F, and this is called the kernel of RKHS, which by the property of RKHS is simply the value of F at this sample point. So basically we first do a sample and then we feed it to an NLP. And this is the construction which is, so this blue curve represents F, and we do point evaluation by taking inner products at different axes using different kernels. And then we feed it into an NLP.
So the sampling operator, it's not adapted to the data anyway, or it's not a Gaussian random sampling or anything like that. It can be any sequencer. That sequencer is not constrained.
Sorry, what do you mean not constrained? So F is a function, and what we want to do is do point evaluation.
So how do you determine the point?
Oh, you mean how do we do this? How do we determine
The sample
location?
points? Yeah.
Yeah, so this is the CIS sequence. Or part.
Sorry, what is the CIS sequence?
Complete interpolated sample. So we always assume that our Hilbert space has at least one such.
Okay, so you know what the CIS sequence is.
Yes.
And that's easy to find. There's never a problem finding the CIS sequence.
Well, that's actually application part, which I'm now very familiar with. Sorry.
That's kind of important.
Yeah, basically, but basically for the theoretical part, we only assume that such sequence exists.
Okay.
And yeah, you could treat our construction as a non-constructed one, because in the end, our proof only states that such not CIS, but sampling-based operator, we can find the sequence of such sampling-based neural operators, but we don't really give an idea of how to find such
Okay,
operators.
so you're assuming you can find this CIS
Yes.
sequence, So first of all, you know that it's always possible in principle, or I guess there's two stages. Do you know it's always possible? And then secondly, how would you actually find such a?
Okay, so the answer is theoretically it is possible, and
Okay.
theoretically we can give a lot of guarantees. And later Yicen will show in practice how to find these
Okay.
things. Now,
So it is, so there is a procedure to find the CIS sequence.
You actually just intuitively treat this as images with the projecting to the fixed point.
Okay, because I guess what I'm thinking about is compressed sensing, where you have a sampling basis that is incoherent with the reproduction basis.
Yeah.
And so it's very important to choose your sampling basis, like a Gaussian random basis and Fourier basis or something like that.
But no, but just intuitively project it fixed point.
Okay, so in the end, it becomes very simple.
Yeah, but not very simple. It's
Okay.
something that they were referring to.
Okay.
okay, so having defined this operator, we now look at how to do the set value problem. So given such an SNO F hat, we can induce from it a family of sets, superlevel sets, simply by feeding the output of F into a sigmoid function or something similar with thresholds gamma, which determines this lambda. And this would be our induced family of clusters. And finally, our main theorem states that there exists a set of SNOs at paths such that their induced clusters do converges to the real cluster, in the sense of the Kuratowski topology. So this all these two all.
Sure. Thanks. Okay, thanks Ruiyang for the theory. So after establishing the theory, so 1 minute, okay, stop talking and just show me how you build the models. So basically, we call this our proposed sampling-based neural operators. They can be roughly divided into two stages. The first stage is like how we perform the discriminations, and the second stage is like how we develop such a deep neural operator architecture for this clustering purpose. So we'd like to firstly start from the discriminations we use, right? Like as we mentioned, like we use a very simple and straightforward method. We just treat the fixed grid, specifically a 2 to 4 times 2 to 4 grid, as our sampling sequence, and then we just take.
What are you sampling? So what is, no, sorry, now you are actually sampling some real data, right?
Yeah.
What is the data?
So it's oh sorry, it's I will introduce later.
Okay.
So yeah, we're firstly trying to this is how we project how we do the explanations. So we transfer the functions into some 2D visualization of the inputs. We can view that this as images. And there are other options, like you can also compute the short time Fourier transforms on the observed trajectories to get some like spectrogram and treat that as inputs as well. And so basically the explanation is pretty simple. We just put the functions into fixed grid images.
Can you say very simply why, so you have a grid of pixels, like a matrix, and y is just taking those so you're taking every value in that grid? So it's a complete sample, or?
Yeah, so like for example, we generate, so like for example, we have solutions and then we just sample several points and then we just map these points into images.
So the CIS is all 224 squared pixels, or some sequence of those, or? Well, so it's a non-uniform sample.
Yeah.
So how do you pick which?
Oh, right, yeah, right.
There has to be some sampling of.
Right, yeah, so we use so like we want to make sure, like, I think in our practice, we just, I think we use like an intersection, like we want to make sure in each intersection we sample a certain points. So like, for example, suppose this Oh, okay, like suppose, I think like suppose this number functions, and then we just create each section, and we want to make sure we sample enough points from the sequence. And then we can just make the plots on it.
And have you determined, you know, the size of the interval?
Yeah, this is just the based on experience. Like this can be like, for example, I just said from just this t, I just said like 0.5, 5 to 10, I select 20 points, something like that.
It's equally spaced or not?
It's equal space. It's equal space, and this can be improved. Like for example, sometimes it has very intensive structure. We can sample more points.
But shouldn't it, if you're using Fourier transforms, discrete Fourier transform, shouldn't you look at the Nyquist frequency or some
Yeah.
spectral, like the bandwidth of the signal or something?
Yeah, indeed. This but I think but this is the so this can be improved. Like basically, we're just trying to show that we use this way, and there are also other options because now the images they are discretization environment. They are not discretization environment. If you choose different grade, then you cannot you cannot get you cannot really use that. So there are lots of options for this discretization process, and we just choose two. We just simply okay. So there's a sequence, and we just for each interval just select some points, and then
But how do you know it's a CIS?
yeah, I think that's a good point. Yeah.
Like you could do something like compressed sensing where you can guarantee that you capture all information in the signal. Or I guess that's what I'm worried about is if you're just like you try some intervals and then there's no real guidance on how whether you've got a CIS. Is there some test you can do afterwards to say, well, this is the CIS or not?
Right. Yeah, well, I haven't come concerned about this.
Okay.
I think we should really look into this.
Okay, so what you're doing now is you try something and
Yeah.
it kind of seems to work.
Yeah.
And if it seems to work, then you
Yeah, seems to work. Yeah, because now it's a super naive version. So like this is simple version, and we can always like add more techniques on that, so that for example we can get an idea.
Yeah, I mean, it would be good to show that yes, indeed,
Yes.
I've got a CIS and
Right.
now I can go for it.
Thank you so much for that point. Okay. Oh, sorry. Right. Okay. Then about the second part, like how we construct the neural layers. So it can still be roughly divided by two parts. Like the first part is like we can see that there are some hidden layers which basically are feature maps, so that we can use a frozen portraying visual encoder to replace this. So it acts like a fixed high complexity nonlinear map which capture the information from the inputs we have. So we can use like transformers or ResNets as these tree models, and we can also don't need to worry about trainers because like it's we can avoid overfitting and avoid training for the features. And there's a last part is the overcast hat, which take the features from the nonlinear map and project it into the cluster space, which outputs the cluster assignments. And this is where the real training happens. So we only need to train this part. Actually, it's a 5-layer MLP, and we use a way named the constructed learning. So basically, like we have images representing for our functions, and then we add prediction on that images so that we can get a perturbed version of the images. Then we just feed through the nonlinear map, and then the overcast tab. And so in the cluster space, they should belong to the same cluster because these two perturbed view are actually generated by the original images orientation for that trajectory. So this is how we train the cluster hat without doing the labels. So it's from the self-supervised approach. And more specifically, this is how we choose the objective functions. It consists of basically three loss terms. The first term is of course entropy, which means we want to maximize similarity between these two perturbed view so that this encourages perturbations within a function neighborhood do not alert to the cluster identity. And second loss is what we call the confidence loss. It's penalized the flat distribution. We want our class paths make sharp decisions, or which also consistent with the theory requirements. We don't want like outputs is some randomness, some union, some flat distribution. So it is equal probability that you assign each category to cluster. Yeah.
Sorry, I'm gonna ask you. So I'm a bit lost about how are the clusters defined? What in this is saying something goes in one cluster, how many clusters are there and how do you assign to different clusters?
Right. So like for example, like we need to predefine the number of clusters first. Like suppose now we know the number of clusters is 6.
Okay,
And then and then we just put all the data into and to generate two different and for each trajectory images for that data set, we generate the pairs of it. And then we pass to the nonlinear map. And this nonlinear map, like for example, the output will be like, for example, d equal to 700 dimensions. And then the job of this cluster head is trying to project these features into the k dimensional space, where k equals to the number of clusters.
is this, okay.
Yeah, so like, yeah, so each element of the outputs stands for some score or probability that, so for example, here means like this trajectory should belongs to the probability that this trajectory belongs to the first cluster. So for example, if it's 0.7, means like there's a like very threshold, then so then this trajectory will be cluster into the first cluster. So that's how it works.
Okay, and what's the definition of a cluster here? That's what I'm, so you define, you're thinking there could be 6 clusters, but maybe there's
Yeah,
120, or
Right.
maybe there's one.
yeah, maybe
and-
this one, yeah.
And how do you, so what makes a cluster?
Right, this is super good question, because like, for example, there will maybe 7, maybe 8, we don't know. So this is
Right.
just a start. This is just a start. So we assume we know the number of
So
clusters.
here, when you're doing this sorting, so it's trying to sort into a maximum of 6 clusters. And how is it doing that? How does it look at that? What determines what goes in what cluster?
So yes, like we use the training, so this is the reason why we need the training approach too. So it will, so like by trying.
Oh, no, you train it on pre-clustered data?
Yeah,
Okay, so what you've got is a training set where someone has, an oracle or something has pre-clustered.
no, we don't need the label, we don't need to know the labels, we don't need to know which cluster it belongs to. We just, because we use this one, because this is the reason why we need these perturbations. So like, because we don't know the label of it, but we know these two belongs to the same cluster. So that's magic that.
How do you know they should belong to this?
Because so for example, you give me a trajectory, I artificially add a perturbation on that image, on that representations. So you can treat as a neighborhood. So actually this is x1 and this is x1's neighbors. And then after projection, this also belongs to the same cluster because they are neighbors.
Oh, I see. So you take a single trajectory and then you perturb them?
Yeah, perturb them, yeah.
And then because you know they're really the same,
Indeed.
and then you know, okay, so that's the kind of the training. Okay,
that's a
I
kind of-
missed the part.
No problem. Okay, yeah, that's how we train this one, and then it will,
Okay.
there are a clustering way.
Excuse me, you mentioned you use a pre-trained
Model, yeah,
model, but adding to that, when you mentioned you use the transformers, right?
right.
And so that, and the role of that pre-trained model is just to provide a latent space for the data.
Yeah.
So how do you know that latent space is compatible with your data? Why a transformer?
So yeah, so good question. So this works based on experience. You can choose other model. You can choose CNN. You can choose. We use control model because we don't need to train that part. So you can use like CNN, you can use ResNet, you can use other like techniques. You can construct a real neural operator to do this task. So for here, we just like
There isn't, so
Yeah.
it's temporal only, right?
yeah.
I mean, there's
Sample.
I'm asking because there are a couple of studies that they claim that transformers are not good for temporal data, for temporal predictions. So that's why.
Right, because like in time series, but there's also like what I tend to use because like in time series data they use like transformer or some structure to predict the temporal data. So that's the reason. But yeah, but of course you can use like for the feature map you can use other options as well. Okay, so sorry. Okay, so here comes our data. So now we propose two different kinds of data. One is OD6, one is OD4. And OD6 refers to we have like 9,000 samples, which including this six different families, like including linear PVP, nonlinear PVP problem, and linear homogeneous problem, and so on. And for each system, we set three different initial conditions, and in total we have 9,000 samples for this data, and we use 80% as training set, 20% as test set.
So your goal here is you have you put in all these trajectories
Yeah.
from all these six ODEs.
Yeah.
And then there's six, there
Yeah.
should be six clusters.
There should be
because you have
six.
the six
Yeah.
ODEs, and what you want is your algorithm to
Distinguish.
know which
Yeah.
trajectory comes from which ODE.
Yeah.
Okay, and so you pick these ODEs, which are quite different.
Yeah.
Is there some notion of feasibility? Because could you give it a wrong, 2 or 3 ODEs that were somehow indistinguishable, or?
Yeah, indeed. We will show later. Like actually, we are not 100% accurate on this one. So basically, yeah, we designed OD6 because like you can see we choose fundamentally different
Yeah.
system, and we're trying to test our model frequently.
So this should be an easy one.
Yeah, it should be an easy one. And another one is like we use a randomized neural ODs, like they will generate very chaotic and very like high, very like very massive intra-class variabilities. So this will include 4 families of the solutions from first order homogeneous to second order non-homogeneous one. And we rule this one to test if our method is robust on especially near the decision boundaries. And so this is how the data looks like after the validation. So basically only 6 we can see they have some fundamentally different problem. And for only 4, like they have like very high intra-class variability. Okay. And so this is our main readouts. So basically, our purpose is not trying to say, okay, we beat this model, we get some best performance. We're trying to show that the cost is feasible by this way, by this neural operators. And so firstly, please look at the first section, like these traditional methods, they may not have a good performance. And then the second section, this is what trying to say, like if we treat this as a pure computer version task, like if we ignore all the background, all the like context, all the theory, like this is the baseline we have. Like we treat this as just a simply an image clustering problem. So you give images and then use a neural network to perform clustering on that. So this is the baseline we have. And it's still just get a maybe 60% accuracy on the OD6. And for the SNO, and it can achieve like around 93%. It's not perfect, but it can distinguish the.
And you're sampling here, sort of what proportion of all time points are you sampling?
Sorry.
So is it a sparse sampling in time of the trajectories? Like your CIS or your apparent CIS is what proportion of points are you sampling? So you're sampling in time?
Yeah, something in time. Yeah.
And if you have like n total points in time, what proportion of those are you sampling?
Oh, right. That's a good one. Actually, we just like for example, I just create like for example from 0 to 105. I just use all the 100% of the.
Okay, so here you're using 100%.
Yeah.
But there's no question of CIS because you've got all the data, all the information.
Yeah. That's
okay.
That's how we.
Have you tried undersampling or?
No. I tried that.
Okay, good.
Yeah.
That's important.
Sure. And okay, and so this is our also some visualization, like for example, if you just split perform paintings on plane features, you get some entangled representation, and if you perform if you see the as an outputs, it gives us a real separate clusters. And so the ODE6, therefore ODE6, the baseline cannot distinguish between the linear DVP and the nonlinear. They cluster into they distinguish at the same cluster, while the SNO method is more consistent with the ground truth clusters. Similarly for ODE4, they just like for the baseline, they just like randomly assign the trajectory to each cluster. And SNO, they only get 60% of it start to show some separable partners. And lastly, we will prepare experiments about the sampling in the solution, because in our theory, we claim that like because I'm not sure this is the same thing, because like we use the sampling resolution to indicate that we try different sampling rates, so that we can generate a sequence of sampling with neural operator from 4 times 4 grades to 2 to 4 times 2 to 4 grade. And so that's this the trend we have, like on all the matrix, we have like if as the increase of the sampling resolution, which may be can represented by the sampling rates,
Right.
our method shows at least shows a trend towards limit towards like a stable point. So which maybe support our claim that okay, our SNO is able to so with the sequence of SNO, our outputs of SNO will converge to the true partition case. And okay, there are still 2 experiments. So here, since we claim that our method is like our loss function is designed specifically for this task, so we want to test out if we remove one of them, do we really need this loss term? So we just do a budget study on the 3 loss term we use. So if we remove the entropy term of a method, it easily gets a model collapse issue. And if we remove one of the entropy loss or the confidence loss of a method, it's a suboptimal performance. So which means that we need 3 of them together to obtain the best performance. And last one, okay. So we also passed the alpha, which we put the loss weight on the entropy loss to control the scale, and we find out that on the training set of ODE6 and ODE4, they show a stable trend. So we just simply set alpha equal to 1 for all the experiments. Okay, thank you very much for listening. So in summary, so in this project, we're able to develop a theory and as well as a feasible assembly-based neural operator to show you that we can use neural operator to discover the functional clusters. Okay, thank you guys.
So in interest of time, we don't ask any questions, but I want to make 2 short announcements. Or one, I want to say something. So next week it's reading week, so there will be no Ames Lab seminar. But then the week after it's Mimi Day from University of Illinois Chicago, which will be here again. And then the week after this, which is March 2nd, there's an empty spot. So I want anyone who wants to present to give the opportunity to present. So if you want, send me an email. Otherwise, I will present my second part of my talk, but I don't want to like take away your thoughts. So if you're really interested, you can present. Yes, and then we can do discussion. So thanks everyone, and see you or have a good reading week.
Thank you.
And